Higher order derivatives. Now this higher order derivatives, we have known that a function is represented by fx. We write it as y equals fx. So when we differentiate it, we write it as y prime equals f prime x or y dash equals f dash x. So derivative is all about finding the instantaneous information of any kind of physical or mathematical function. Okay, so we use the derivative for that. Now the question arises is what is higher order derivatives? So a higher order derivative, it refers to the repeated process, means not once but multiple time taking the derivative, that is derivative of a derivative, then derivative of derivative, that is y equals fx. We write dy by dx as f dash x. Now we write this as y prime. This we already know. So higher order derivative is the differentiation of a derivative. That is d by dx of dy by dx is nothing but the higher order derivative. So we can write it as f double dash x equals y double dash, or you can say y prime double prime. So this is the first derivative, this is the second, third, fourth, fifth. So the derivatives other than first derivative, they are called as higher order derivatives. The second question which arises is what do higher derivatives tells us? What does this signify? So this higher order derivatives, the second derivative or the higher order derivative, this can measure the various physical parameters, for example acceleration of a moving object, or it can help to optimize various algorithms. For example, you have a car. Now when it is moving, it has some speed and velocity, but when it has speed and velocity, it will stop also, it will accelerate also at an intersection. So that is the rate at which the speed changes can be achieved or can be calculated by this higher order derivative. There are different speeds, 100, 60, 20 like this. So there can be some global maximum, global minimum, but there can be local and local maximum minimum also. Okay, that is governed by higher order derivative. Now higher order derivative in real life, so if you see the same example we'll take, we talk about cars, plane, roller coasters, and there are many examples here. So the higher order derivative means the derivatives other than the first derivative and are used to model the real life phenomena. For example, the transportation devices, as I just indicated. So there is a position called say s function of t. So when you take the differentiation of this st, that is s dash t, it will give you the velocity. So the differentiation of position is velocity. Now in order to get the acceleration, you have to differentiate the velocity. So the differentiation of velocity is acceleration. So position differentiation is velocity, velocity differentiation is acceleration. So you can say that acceleration is nothing but the higher order derivative of position. I hope you got the idea. So as we have seen that the velocity can be considered as the first derivative, acceleration can be considered as the next derivative or higher order derivative. So there is another way of looking at it is that acceleration function is actually the differentiation of position function twice. So position function differentiation will give you velocity, velocity differentiation will give you acceleration function. So the function acceleration is nothing but the second order derivative, or you can say higher order derivative of the position function. So it is not represented by 1 prime, it is represented by double prime. So s double dash t. So the second order derivative is an example of higher order derivative. Alright. So the third derivative is the derivative of the second derivative. The fourth derivative is the derivative of the third derivative, and likewise. So as we are discussing about the acceleration issue, let us take an actual real life example. So because the moon has no atmosphere, a falling object on the moon encounters no air resistance. This we already know. But now in 1971 what happened? There was an astronaut. In 1971, David Scott, he demonstrated that a feather and a hammer, they fall at the same rate on the moon. So when they are falling at the same room, that is same rate, we are talking about a function, a position function, and that is in meters. So the position function of each of these falling objects is given by certain function. We can represent it by say s position and t is the time, vt is velocity, at is acceleration. So this is the position function, s, that is the function of t, is minus 0.81 t square plus 2. And in order to show them or this function graphically, you can have a graph like this also. So someone asks you what is the acceleration due to gravity on moon, or what is the gravitational force of moon when this st function or the position function is given. So the gravitational force on the moon can be computed easily by double differentiating this function as we just discussed. So st we already have, This is a position function and it is already being given by minus 0.81 t square plus 2. So let us take the differentiation that will give you us the velocity. So s dash t is minus 0.81 t square, differentiation is 2t, differentiation of a constant is 0. So what do you get? 2 into 0.81 will be 1.62. So it will be negative 1.62, 0 will not be there, and there will be 1t. So this is a velocity function. Position function, now velocity function. Now in order to get the acceleration due to gravity on moon or gravitational force on the moon, you have to differentiate s dash t again. So you need to have find the higher order derivative. So s double dash t is nothing but, see, there is only one t. So d by dt of t is 1. So you only get minus 1.62. So minus 1.62 meter per second square is the gravitational force on the moon. And if you want to actually do it on a copy, you have to do it like this. Position function you have to write like this, velocity function like this, and the acceleration function. Finally you will come to a conclusion that the acceleration due to gravity on the moon is nothing but minus 1.62 meters per second square. Now let me take a very simple example that is pertaining to your book. Normally this is how you are going to get question in your exams or to solve. X cube plus 10x, so I have taken a algebraic function also, I have taken tan x, that is the trigonometric function also. So let us represent it by y equals x cube plus 10x. So when you take fx, this f dash x we have to find out, or y dash we have to find out. This x cube will be simply 3x square. You know the differentiation. I hope that you know the differentiation, then only you will be able to understand the higher order derivative. So this will be 3x square, tan x differentiation is x square x. We will differentiate it again, d2 by dx2. So f double prime x or y double prime, 3x square, 3 will be there, x square will be 2x, sec square x will be 2 sec x tan x. It is considered as the x sec whole square. So 2 sec x differentiation is sec x tan x. So what do you guess? 3 into 2x is 6x, and 2 sec x will be sec square x, so 2 sec square x, and then we have the tan x. So this is your higher order derivative, or you can call it as second order derivative. So in order to solve in your exam and how we are going to write it, this is the way you are going to write it. That will give you the complete marks. So I hope you have a better idea of higher order derivative now. Thank you so much. Take care of yourself.